All right. So, hi everyone. Thanks a lot for coming. So it's a pleasure to have Ulrich, our speaker today, and we also have Harold, our panelist. So he will be discussing at the end or asking some questions about the paper of Ulrich. So Ulrich, you have 1 hour, and so he will be presenting projection-based wide bootstrap under general two-way clustering dependence with serial dependence. And so again, you are welcome to ask your question during the presentation. So you can directly ask the question. So I will, unmute you, or you can do that, or you can, if you prefer, post your question directly in the chat. So again, thanks a lot, Ulrich, Harold, and so the floor is yours.
Thank you very much for having me in this seminar series. Yes, I'm going to present today a projection-based wide bootstrap in a context where we have a cluster dependence, and in particular, one dimension, we have a serial dependence. As motivation, we know that multi-way clustering is become very important and challenging in applied work. And take care about the dependence is relevant, if not result. You could end a great paper with misleading inference, as Bertrand and co-authors highlight in the paper. In this paper, we focus on a particular kind of dependence, a cluster dependence, and the cluster dependence can happen in more than 2 dimensions, but we focus on 2 dimensions. Why is it relevant? Because in different fields, in economics, we have those kind of data, and we need to handle the dependence in the data. Then in particular, in my talk today, I will focus on a bootstrap inference, okay? Then I'm just going to introduce the setup. We are in we consider a linear model, okay? And we have 2 indices. One is I and one is t. Then in particular here, t is for the time dimension, and we allow serial correlation. But to give an idea, I will focus on the simpler independent context. Once you understand this context, taking care about the time dimension becomes easy, okay? The OLS estimator beta hat, as usual, we can rewrite in this form, where beta hat minus beta is equal to these quantities, and we have the score, the sum score here. Then basically, our goal is to study the limiting distribution of this OLS estimator, but in this general context where we may have cluster dependence. And we follow the literature, okay, and we consider a general Aldous-Hoover Kalbenberg representations, where f is here is a measurable Borel function, and we can represent the YIS and the disturbance UIT as follow, where what is relevant here is the quantity alpha I, psi t, and the epsilon it are mutually independent random variable, okay? And psi t is a stationary, but could be serially correlated, okay? This representation is general in the literature. And once we agree on this representation, the like I said at the beginning, the OLS estimator can be represented like that. Then to study the limited distribution of these quantities, we'll focus on this guy. And once we know how this guy behaves, then things become very easy to follow. Then this quantity, the sample score, can be decomposed in those 5 elements, okay? Where what is important here, the quantity AI, DT, VIT, and epsilon IT are uncorrelated. As you can see, basically AIT, we project on this dimension, and we subtract with mean. And then when you take the expected value of this guy, it will be 0. That's something usual in the literature. With this representation, basically, of course, with real data, we cannot observe those quantities, the A, the D, and the nu and the E, but we will look at the sample analog of those quantities when we want to do inference. But knowing the behavior of those quantities is important to derive the asymptotic distribution of the OLS estimator. Following Menzel Econometrical Paper 2021, we impose these conditions. Basically, we assume that each component has the spectral decompositions defined in this equation 3. And based on this decomposition, we can define the variance of each quantities, what I denote by sigma square A, sigma square D, and sigma square V. And with those notations, remember again that, as I told you, our goal is to know the behavior of this OLS estimator. Then in particular, this will converge to, in probability, to a quantity under some smooth assumption. But now the distribution mainly will come from these quantities. Then we want to, based on, with our notation now, we want to rewrite these quantities. For example, a score, we can rewrite this quantity based only on the assumption I made here, this decomposition, and the spectral decomposition. We can rewrite as follow, equation 4, and that's very important. This equation 4 will drive the limiting distribution of the beta hat, the OLS estimator. And you can see we have this first quantity, which is a function of A, which I denote by ZA, and the second quantity, which is function of D, and the third quantity, and the Hadamard product quantity, which is here, okay? Intuitively, this decomposition, okay, this decomposition in the equation 4, what can we say? We can say that because the Z here is a Gaussian distribution, then the decomposition said that the beta hat is the function of some independent Gaussian distribution and also some product of Gaussian distribution. Okay, then the behavior of this SAM score will be, when we focus on this equation 4, we have all information we need about the asymptotic distributions, okay? Then in particular, given the condition, remember that I defined some variances at the beginning, sigma square A, sigma square D, sigma square E, and sigma square V, okay? Then the asymptotic distribution of this SAM score will be depending on the behavior, the limit distribution of those variances. We have different asymptotic results. Some of them will be Gaussian, some of them will not be Gaussian, and the behavior of the quantity T sigma square, the limiting behavior of the quantity T sigma square A and the N sigma square D will give us some information regarding if we have some clustering in at least one dimension, if the clustering is, the dependence is persistent or not, or if observations are basically independent over the intersection and so on. Then let's start with the first case. Okay, we have clustering in at least one dimension when in fact we are either in equation 5, either T sigma squared diverge or T sigma squared T sigma square A diverge or T sigma square D diverge, okay? And this condition implies basically that the underlying DGP has some persistent clustering along at least one dimension. It could be the dimension of I or T, okay? And in this context, the asymptotic distribution of beta hat will be dominated by those two quantities. Remember that this quantity, we have this guy here, the ZA, ZD, ZE, and the Hadamard product element, which are here. Then in this context, those two quantities will dominate the limiting distribution of beta hat, okay? And
sorry,
yes.
just to clarify very quickly. So here, are you thinking about triangular array, or is it a fixed DGP?
It's not a fixed DGP. It's
okay, so these variances can be sample size dependent. Is that right?
What is the sigma or what?
The sigmas or the DGP, you know, your representation basically.
Yes.
Okay, I see this.
Thank you. And in the second scenario, remember that here we say this diverge, T sigma square AF diverge. Okay, then in the second scenario, when we assume that this converge to zero, okay, we call this clustering effect vanish. Okay, then basically in this context, the contribution from the clustering in both dimensions is not too important asymptotically. Okay, then in this case, we have two sub cases. Okay, and what will happen in the context where this quantity without multiplied by T is different from zero and positive, certainly greater than zero, what will happen is that the asymptotic distribution is dominated by a non-Gaussian component, and then the asymptotic distribution of beta hat is not Gaussian. Then in this context, if you use the usual way to do inference, you could have what I mean by usual way to do inference. You compute like the quantile of the Gaussian distribution to do inference, and even you have a standard error which is robust for autocorrelation. You may have misleading results because the distribution is not Gaussian. Then we should not use the T distribution or something to do inference, right? Then this is one context. The second context is when sigma square nu without multiplied by T or N is asymptotically negligible, then we are basically in the context where we may think that the interception element the DGP is cluster meaning at the intersection level, okay? The third scenario, the fourth scenario and the fifth scenario can be seen in a context where we have clustering at intermediate strength. Basically, the limited distribution of sigma square A, when we multiply by T, is not diverging and is not going to zero. And N sigma square D also is not diverging, but converge to a quantity which is different from zero, okay? Mu A and mu D. Then in this context, we have clustering at intermediate level. But the behavior of a limited distribution, again, will be derived by sigma square nu F. Depending on that sigma square nu F is strictly greater than zero or asymptotically negligible, we have different results. The easiest one is when it's asymptotically negligible, that's the usual scenario, and the asymptotic distribution will be Gaussian, basically. But when it's greater than zero, we are in a more complex situation. The distribution is not Gaussian, okay? Then when we characterize the, we took time to characterize the limiting distribution by basing on this quantity, because when we know well this limiting distribution, is become easier to approximate it or to figure out if it's possible or impossible to have a feasible result to do inference. Okay, that's the idea.
Well,
yes.
Sorry, just to clarify. So this equation 4, is it exact, or do you have some approximation error? Because the left-hand side is not necessarily Gaussian, right? But you're talking about the right-hand side has these Z components that are Gaussian. So is it approximately true, or is it exactly true here?
Good questions. Is exactly is a representation, right? Is a
Okay, so that's just
is yes, is just is exact. It's like equivalence. It's like because this quantity we can always rewrite after you agree on this decomposition or this representation. We can always rewrite in those 5 components. Okay, but now we don't know. Okay, we don't know which component will dominate. Okay, depending if we have t multiplied by sigma square, then some of them will become negligible, and then we can put plus small o. But here is just exactly. But now when we are in a context, depending that t multiplied by sigma square is going to 0 or going to infinity, then some of them will disappear, or we could still there, and we can add some negligible term. But here now, it's just a definition of the components. Thank you.
Sorry, I got confused by notation, but yeah, I understand now. Thank you.
Great, thank you. Then with those representation now, as I said at the beginning, our goal is to do the inference, right? And by the way, Harold and co-authors, they propose one important paper in this literature where we are basically in the same context, where we have 2 dimensions, and the one could be time dimension with a serial correlation, and they propose a robust way to compute standard error, and to connect my presentation to the paper. The main difference is basically, as implicitly in the paper, they assume that we are in a context where the limiting distribution, okay, of this quantity will be Gaussian, okay? And then when the limiting distribution is Gaussian, because when the limiting distribution is Gaussian, it's become relevant to compute the standard error, and you can do inferences. But if it's not Gaussian, you compute standard error, it may not be useful to move forward, right? And but then in our context here, of course, we consider the case where we may not have Gaussian asymptotical distribution, and as you can see shortly, we may not also be able to do inference. Okay, there are some situations where, and this has nothing with Bootstrap, okay, where we cannot do inferences because there is no way to estimate some quantities in those contexts. But I will become more explicit in a few minutes. Okay, then we review different scenarios of the asymptotic distributions. Then again, in this paper, our main goal is how can we implement a Bootstrap such that we can mimic this asymptotic distribution even when this asymptotic distribution is not Gaussian, in case it's not Gaussian. And the Bootstrap, we propose what we call projection-based wild Bootstrap. Basically, is defined in equation 8. And here, the empirical score is defined by S hat IT. And you can see that in 8, we have 1, 2, 3, 4 quantities. And if you remember, we define at the beginning, I say that this decomposition is important, okay? This score decomposition, U is the true disturbance we cannot observe. Then those quantities are invisible. We don't know those quantities. But when we come to the Bootstrap, we are going to compute the sample analog of those quantity AI, DT, VIT, EIT, and the sample analog of this expected value is just the sample mean of this score, right? Then this is what we are doing there, and then we want to do a Bootstrap. Then you can see that here, of course, in my definition, W by definition is the sum of VIT and EIT, okay? Then that's what we call WIT. Then in the sample analog, we want to compute the sample analog of those quantities. And then you can see one difference is I multiply by some quantity here, eta I star, eta T. Okay, those are some random variables. This is what we call wild Bootstrap. We draw some random numbers and we multiply by some observations. But here we are not multiplying anyhow, okay? We are multiplying in a way, you can see that the same eta I I'm using here, when this comes to this WIT, is the same eta I here, and the same eta T I multiply with the component on the T dimension, I multiply the same eta T here, okay? And here we use what we call Radmacher distribution. Is a distribution which takes the value, -1 plus 1, and with some probabilities, 1/2, 1/2. And we are in a context here where we say that we allow serial correlation over T. Then by just drawing the eta T IID, this may not be able to, to capture this serial correlation. But we propose a way to generalize the Radmacher distribution idea with some serial correlation. You just need a kernel and you choose appropriately. But the main idea here to understand, once you understand how this works in the independence case, the other time series will follow. Okay, this representation is very important. That's the way we propose to generate the Bootstrap score-based observations. Okay, then once you compute what the quantity equation 8, you can compute your Bootstrap OLS estimator, and then if you want to do hypothesis test, you compute the quantity, which could be a linear combination of if beta is a k-dimension vectors. You take a linear combination depending of your null hypothesis, okay? And then you base on this quantity to estimate the distribution of your original statistics. That's the idea of a bootstrapping. You can also compute confidence interval if you want, okay? Now, that's the idea of the bootstrapping, okay? This look easy, right? But now let's try to see how we can implement it, and if we can always implement it, okay? Then, as I said before, the quantity, those quantities here, A hat, D hat, are the sample analog quantities we define from the score representation. Then we can rewrite the sample score as follow, where we just, of A dot I, we center, we take the sample score, and over where we take the average over T, and we demean, and similar for the other quantities. Now, equation 10 is provide the main idea of how what we are going to do here. This A hat I didn't tell you exactly how you are going to compute, right? But let's start gradually. We'll start with what I will call infeasible scenario, okay? Assume that we can know the true variance sigma AF, sigma DF, and those quantities. If we know those true variances, how could we approximate the distributions? Okay, if we generate the bootstrap observation like that, but we make sure to preserve a serial correlation by generating eta t non-independently, and also we generate eta I like the usual rad measure, and we also now put a stronger assumption. We cannot observe a true DGP. We don't know the underlying DGP, but we think that we can know the true variances. Can we mimic the distribution? Then we'll move gradually, and then we'll see where the problem will come from, right? Then we start with this scenario, and then in this scenario, when we generate the A hat I like that, and we assume, of course, new A and new D are some scaling term which depend on the true variances sigma AF and sigma DF. Okay, with those notations, and as we highlight at the beginning, the asymptotic behavior of beta hat will be function of how T sigma square A and N sigma square D the limiting property of those quantities are asymptotically negligible, or diverge, or converge to a non-zero constant, right? Then in this scenario, we show that by using this way to resample, we can perfectly mimic the asymptotic distribution. Whether the distribution is Gaussian, non-Gaussian, it will work. But of course, you will tell me in real life, we don't know those true variances, sigma square A and sigma square D. Then we cannot implement this bootstrap in practice. But at least showing the asymptotic validity of this bootstrapping will help to understand what we can do and what we cannot do. Okay, that's the main idea. Any questions so far?
No question, but I have one. So these sigmas here, so do they? So they determine, I guess, the level of clustering in your data, right?
Yes, but not the level. They provide some idea about if you have a clustering,
yeah,
or you don't have a clustering at all.
Yeah, yeah. So that,
like I said, for instance, when this happens,
sure.
When you have like equation 5 happen, when you have T sigma square A diverge, this provides information that at least when you have either this one or this one, then you know that at least you have clustering in one dimension. Okay. Then when this is negligible, okay, then this means that in fact you could ignore the clustering in this scenario. Then if this provides an idea about the clustering, the strengths of a clustering dependency in your data. Okay.
Yeah. So that leads me to the question whether, I mean, is there a need for like sort of testing for clustering? Because, you know, my point here is, you know, using this bootstrap approach versus the asymptotic. So I guess when maybe there is no clustering, maybe it's more, I would say, you know, efficient to use asymptotic, or so do we need pre-test for clustering? Or
yes, basically we could do that, but that was not the goal of the paper. Of course, there is I think there is one paper where they propose if you want like doing testing for clustering, the presence of clustering dependence, all right. But implicitly, as you can see now, you will see in 2 minutes. I know for people that don't like, some people that don't like pre-testing. You do the pre-test, because when you do a pre-test, you know, you have some randomness first, and then before you will do. But as you will see, the bootstrap resampling, this bootstrap resampling, which is general, implicitly use like a pre-testing, because as I told you, the behavior, we have this quantity here, and depending of the behavior of sigma square A, sigma square D, and one could be dominant, and one could be negligible, and the distribution may not be Gaussian. Then we incorporate those information such that you are not going to use a specific way to do like you are not going to assume, oh, I don't have any clustering, then I'm just going to do the same resampling. But this general resampling will capture all scenario at the same time, and then you can move forward.
Including the the Gaussian case.
The non-Gaussian when
the
non-Gaussian, but when the non-Gaussian case is not in all scenario that we can have a feasible result. This has nothing with Bootstrap. There is some context where it's impossible to estimate the distributions, okay, and we will see. But when it's non-Gaussian and we can estimate the distribution, then this method can do that as well.
Okay, good, thank you.
Thank you. Then I introduce the general method, but I told you that unfortunately in practice, we cannot know the true variance sigma square A and sigma square D. Then to have something which becomes feasible, we need to know some estimator of those quantities. When we can estimate those quantities and they are consistent, we want to replace the true variance by a consistent estimator and see if our method will work. That's just the idea, right? Then also given the question we just asked, we implicitly use the idea of a pre-testing to know in which regime we are exactly, such that we know which component is the dominant component, okay, by putting some indicator of function, and this is what I'm going to explain now. Then the first feasible approach, which we call projection-wide bootstrap feasible approach, the general one, you replace the unknown variance by a consistent estimator of the variance. And now, and based on that, we want to discriminate different scenario, okay? And then the first one, we call projection-wide bootstrap the divergence case, okay? Then when we assume that the quantity sigma square A and sigma square D are converging to, it's not we assume, but we think that we are in a scenario where this converges to a non-zero constant, then we need to estimate the quantity mu, which should be denoted by mu hat, and mu hat A and mu hat D. And then we advocate using logarithm of t divided by t and logarithm of n divided by n for those quantities, and this satisfies the condition, and this works perfectly. The second scenario, which we call vanishing sensitives, basically remember that we have a scenario where t multiplied by sigma square A is converging to 0. Then in this context, we propose using mu hat A equal to the inverse of 1 over t log over t, and this will satisfy all conditions, and it's also work perfectly. Then I will summarize in a table shortly, and it turned out that in fact, when you do your bootstrapping based on this one or this one, you cannot capture all scenario, and basically this will work in all contexts where the underlying DGP provide a beta hat OLS estimator, which is asymptotically Gaussian. But when it's not Gaussian, this may not work always. Then we propose what we call the hybrid version, which combine in a smart way the PWB diverging and PWB vanishing version, where is basically the the quantity mu we want to estimate, remember what I'm talking about. Remember that we say this limit could be a quantity here, and this quantity could be 0 or non-zero or could diverge, right? That was the idea. But in the context where it's not diverging, then we propose now to use this linear combination where D star here is, we construct this star based on a Kolmogorov-Smirnov normality test. And then we show that by using this hybrid version, you can capture all feasible way where the asymptotic distribution can be estimated consistently, okay? And I want to emphasize relationship with our method. Recently, in a forthcoming paper of in econometric theory, there is a resampling method called adaptive wide bootstrap, and this method, our proposed method is related to this method, but still we have some key differences. Okay, as you can see in our context here, we add this indicator function D star based on the limiting distribution to adaptively select the appropriate asymptotic distribution, asymptotic regime. Remember the 5 regime I showed you a few minutes ago. And we also introduce a scaling adjustment, mu hat, and which help us to know either the variance components to control basically the bias of the variance component in each dimension. And we propose a data-driven way to choose the tuning parameter. Remember that I told you that the eta t here, we should not generate as the usual Radmacher, which are independent, but because we want to capture the serial correlation, we select in the appropriate way which capture the serial correlation by using a kernel and a few adjustments. And we propose a way to choose the bandwidth, which we use in this to generate this random variable, so that we can minimize the mean square error of the asymptotic variance. Let me present the main results. We show that by using this general bootstrap-based recent procedure algorithm, we can estimate the distribution of the OLS estimator, okay? And we showed that this result holds uniformly when you use what I call infeasible bootstrap, ideal bootstrap, where you assume that you know the true variance. Of course, we don't know the true variance in practice. But when we use the variance, and remember the variant PWBD, D is for diverging and V is for vanishing. In this, when we use the PWD, the result holds, but is not uniformly over the whole space B. Okay, and when we use the W, remember, let's refresh our condition 5 and 6. Remember, this condition is for diverging and 6 is for vanishing when this tends to 0, just to refresh our mind. Then the important result is all those results are important, but one, I would say, I need to draw your attention on that. This result say that this result we have here, we cannot find any procedure, okay, when condition 7 holds with sigma square V slightly greater than 0, and we don't have any further information on the underlying DGP. Okay, when this is the case, we cannot achieve uniform consistency over the whole space of the function of a Borel function B. Okay, and that's very important to know. This table summarizes all results, and I think this table is easy to follow. We have some notations. Remember that I told you 5 scenarios. That are the 5 scenarios. One, the first, second, third, fourth, and 5th scenarios. Okay, when in this notation, CHS is the variance estimator of Harold and co-authors. And MWCB is a bootstrap method I propose with my co-authors, my student Jiahao is forthcoming at GBS paper. And the other wild bootstrap is the one I just told you, which is a procedure proposed by Geodis which is forthcoming at econometric theory. And ideal PWB is of a method I call infeasible method, because this assumes we know the true variances. Okay, and as you can see, when you have a check, this means that this method works in all those scenarios. Okay, and the PWBD, which basically use a pre-testing and assume that the dependence is the T sigma square A is diverging, or N sigma square D is diverging. This will work basically in the context where you can see that this is working only in the context where condition 6 hold or condition 5 hold. And this is true when the asymptotical, that's our beta hat. The addition is Gaussian here, then this is working in this scenario. In this scenario, the addition is non-Gaussian, but our bootstrap is valid here, and the addition is Gaussian here, and is also valid here. For the vanish case, the PWB vanish, which is another alternative where we assume we put the indicator function so that we can capture that T sigma square A is asymptotically negligible. It will work only in the Gaussian scenario. In this Gaussian scenario, 3 and 5. Okay. Whereas what is become interesting is the PWB hybrid, where we take a linear combination, a combination of the diverging and the vanishing appropriately. This work in all what I will call feasible scenario. Okay, and we show that basically in this context we cannot estimate the distance. We cannot have a feasible way to estimate the variance of the distribution of the estimator. And then, okay, one thing I want to add, of course, the other wild bootstrap, where you compare to the hybrid version, you can see that the other wild bootstrap is not valid in this non-Gaussian case. Our method as well is not valid in this non-Gaussian case. And but this Gaussian case, the other wild bootstrap is not valid, but our method is valid here. Okay, and also compared to my previous bootstrap method, which we call multi-way wide cluster bootstrap, this bootstrap method was introduced by assuming that the distribution is Gaussian, and you can also this bootstrap work in different scenario where you base on the T statistics, okay? But when you base on the non-central statistics and you don't have further information on the underlying DGP, it may not work in some scenario. Whereas this bootstrap, even if you consider the non-central statistics, is work in all those scenarios, then you can see that it's become like more general, okay? Let's provide some comments. Any questions for me so far?
No question for the moment.
Okay. I think I already discussed those results, but what I want to highlight is the following. Okay, based on our results, we derive, we refine a result which was in the econometrical paper of Menzel 2021, where in fact he showed that it's impossible to uniformly estimate the limiting distribution of I think he focused on the sample average, but the sample mean, but this hold also for the OLS estimator, which basically can be considered as an average when we forgot the scale S prime S component. Then we refine his results in a way where in this paper it's like you can think about like a Menzel show a result on a larger set, like we cannot estimate uniformly the asymptotic distribution when some condition hold. But in this paper now, we refine because we narrow this set and precise and figure out in which sub scenario this is impossible to have a feasible estimation uniformly of the asymptotic distributions. Okay, and that's become important because this helps us by saying that don't waste your time to try to figure out that you can find a bootstrapping or you can find a feasible way to estimate the distribution in this context. Okay. In this table, in this table, you can see that when we consider PWD and PWV, we have this scenario, this scenario, and this scenario where we cannot estimate it. Okay, but we can see that, in fact, we show that when either sigma square VF is still greater than 0, okay, or we have clustering at the intermediate level such that, again, sigma square VF is different than 0, it turned out that it's impossible to discriminate the case where the regime where PWB, let's go move back here, you will see what I mean. You can see that this one is infeasible, right? But we have this guy when sigma square nu f is greater than 0, or we are in this context where sigma nu is greater than 0. But in this context, remember that we say clustering vanish, but this context is at intermediate level. But when this condition holds, this I hold in this general context, or this hold in this general context, we cannot dissociate based on real data. Okay, and that's unfortunate. But this has nothing with our bootstrapping. And then what that means in practice, people cannot say it's impossible to identify in which of those sub-regime they are based on real data. Okay. What else I want to say here? I want to say that, okay, our method is a general method, but let's make some connection with the econometrical paper of Menzel. In Menzel paper, of course, he didn't take care about the serial correlation, but in the context where we assume that we do not allow serial correlation, and we are just in the two-way dependent context, we can say that our PWB diverging method, okay, shares some in terms of properties, share some result with a Menzel approach, okay? But the main difference is, of course, Menzel method I didn't introduce at the beginning, but the idea is not far from our bootstrapping, but the main differences is that Menzel methods combine means the usual ifront IID bootstrap with the wild bootstrap. But here you can see that we didn't combine any IID bootstrap or block bootstrap. We just focus on wild-based approach, but we do the resampling appropriately in a way to capture all those kind of dependencies in our data. Okay. What else I want to say? I think again, in the context where we do not have a serial correlation, I think to make the connection, basically the well and popular Cameron and co-authors cluster robust variance estimator is basically, I would say, the estimator proposed by Chiang and co-authors. Basically, I would say, is the analog where they take care of the serial correlation in this appropriate and smart way. The same idea, if I want to make the relationship, I could say that the cluster-wide bootstrap we all know. This paper now try to stay on the wild bootstrap-based approach, but in like a more complicated context where we want to take care about the serial correlation and we want to take care about the fact that the asymptotic distribution may not be Gaussian. And then in this context, how should we do the resampling? Okay, and to illustrate our approach, okay, we simulate a different DGP, and the idea of the DGP is basically to capture all 5 scenarios I introduced at the beginning. Then, for instance, when we consider DGP 16, we'll be in a context where this condition will hold, and then based on the summary result in the table, we already know if the assumption will be Gaussian or not, or what will happen for the different bootstrap. Then this figure summarizes results, and I didn't represent this. The 15 case is, I would say, the case where at least we have clustering in one dimension, and almost all cluster robust base inference work in this scenario. Then I didn't report this here, but our method is also working perfectly. One thing I want to highlight here is basically those results, like equation 16, to refresh our mind. Equation 16, we are in this scenario. Okay, equation 17, where sigma square nu is asymptotically negligible, is for 17. Then I just wrote the equation here. Then we can see that our hybrid-based projection-wide bootstrap approach is working almost well in all contexts. Okay, and what is the main idea here? Of course, given that this method is general and that we didn't specify like we didn't specify like we are in a context, or we assume that the asymptotic distribution is Gaussian. When we know this information, we could do better. We could refine the way we do the resampling. But the method, this method works in all scenarios, whether the asymptotic distribution is not Gaussian or not, and as long as the asymptotic distribution can be estimated, because we have some scenario where it's impossible to estimate uniformly the distribution. But when we can do that, it's worked perfectly, and this can be, you can see here. Let me conclude. In this paper, we propose a Bootstrap, a wide Bootstrap-based approach, where we are in a context where we can have a cluster dependence in two or more dimensions, and one dimension is a time dimension, and we allow serial correlation, and we derive some conditions. Then our one main result is that we try to we study the limiting distribution of the OLS estimator, and we provide some different conditions which can allow us to know if the distribution is Gaussian or non-Gaussian, or if we have a clustering at least one dimension, or we don't have clustering, or basically is at the intersection level or not. And based on these those results, we figure out, we narrow one important result derived by Menzel in a chronometric paper, where he showed that it's impossible to estimate uniformly the limiting distribution of in presence of multi-way clustering. And then we further narrow and extend this result by identifying a subcase where this uniform estimation result is not feasible. There is no way to estimate it. Then we narrow this set, and we provide a projection-wide bootstrap approach, which one we call hybrid version, which so far in the literature is the one which can cover almost all feasible scenario where the distribution can be estimated. And we assess the finite sum property of this procedure, and it's working well. And we also have an empirical result, which I didn't present today. Any questions?
Thank you very much, Ulrich. So now it's it's time for questions, and maybe I should start with Harold if he has any comment or question about the paper. And but again, thank you very much, Ulrich, for the great presentation and paper.
Yeah, well, thanks a lot, Ulrich. So I have a couple of comments, and maybe. So, well, the first one is, so essentially, you are concerned about uniformity, right, of the distributional approximation and inference.
Yes.
You want exact size. So